Okay, dear colleagues, let us start our seminar. Today, our speaker, Anton Pribytok. Okay, let us start.
Okay, yeah, thank you for introduction. Thanks for invitation. So today I'd like to discuss some of our recent progress, which is joint work with Dmitry Bykov, and some of the ongoing progress, which is related to other directions with respect to the problem I'm going to present today. So my main topic will be supersymmetric deformations of the CPN-1 sigma model. And in particular, some of its properties like renormalization, group flows, and conformal limits. So in fact, my main motivation towards the approach of this problem is to construct certain techniques which would allow to study properties and certain objects which are not accessible by sigma models within the sigma model techniques themselves. So let me start a bit with the motivation. So I'm going to describe certain chiral QFT approach, then to develop a unified supersymmetrization, somewhat unified supersymmetrization scheme. Okay, and which will be helpful in understanding and studying anomalies arising in this series, especially at the quantum level. Also today I will stay classical, within classical background, and the so-called beta function exactness. When in supersymmetric setups, people can compute certain observables like beta function, which due to certain phenomena become exact. Mainly, that's one loop argument. Okay, and finally, I want to discuss and understand geometric interpretation variety of limits and mappings. Okay. So let me recap a few things. What the sigma model is. So suppose we have a category of spaces which include smooth manifolds M, and I'm working in the space X. Which in this case corresponds to the d-dimensional Riemannian manifold. Which is also called, in this case, the target space. I will be more specific in a minute. Okay. And at the same time, which is also equipped with configuration space. Of certain fields, or submanifold, if you want, over sigma, where them together define map in space, or maybe for the audience, especially people in algebraic knowledge, like map in stack. But physically, what it means is that you just have certain Riemannian manifold X, you have certain structure in it, and you have X-valued functions which live on this sigma. So what it means? So a generic two-dimensional theory like this can be defined through an action in the following form. GMN, let me write it down so that a bit more specific. X and D, X. Yeah, and well, in principle, one can also have an additional term. Yeah, that's of course an X with dx, 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 mn. Okay. Well, if actually what it means here, you have probably I just recap and say in words, since many are already probably familiar with this. This is called the topological part with a B term, and this is the antisymmetric tensor. A and B's run just from 1, 2, so they live on the wall sheet. So I have a certain wall sheet embedded into this larger space, and my GMN is the metric of my target space, and my H is of course the wall sheet metric. People immediately recognize like the Polyakov type action, right? So in this regard, for today, I will restrict probably mainly to this part, but this is just because I'm studying a particular class of the models that I'm interested, especially, like I said, in the deformation of certain deformations, in particular integrable deformations of sigma models, what it means, and a canonical example, just for me to maybe to remind you in which sector I will be lying on. This is the so-called Fateev-Onofri-Zamolodchikov. Okay, let me quickly just recap what I'm talking about. So this is, again, as you can imagine, sorry, yeah, now this is dx plus dy dy is a of t plus b of t. Probably there is a 2 and the cosh of y. Okay. Of course, let me just recap. So these are the fields that live on my target space, and these a and b, which depend on a certain parameter t greater than 0, and those are effectively the parameters that are associated to the description of the geometry of your target space. What it means, in fact, of course, I should be more precise. Maybe some people are more familiar when you add this, like a topological term. So you can have a theta term with a of this form with an t instanton number, which is can be explicitly constructed in these terms. But for the moment, I just restrict to this. And what it means is that, yeah. So these A and B parameters, what I'm talking about, this t is the time. So not to confuse when people studied the like renormalization group flows where you have a certain scale, but here this is the time flow. So effectively, this is your RG equations describe how your geometry flows. So this, in fact, this is Ricci flow. What this model describes is that if you start, okay, let me be more specific. So again, like in previous terms, if you don't have like even locally you can have, but if your curvatures are not too big, you can study perturbation theory, and in fact you can your theory gets renormalizable, and so that it leads to the perturbation leads that you can get the renormalization group flow, which is one loop renormalizable, which is taken the simple form. Okay, which is sufficient due to huge symmetries here. In fact, this is of course the Ricci tensor, but it is sufficient just to, as it was shown by this gentleman, that you can study all this RG huge system reduces just to something very basic, and effectively what it means, you almost trivial. You just get this pair of equations. Yeah, AB. Okay, or what I can effectively do is that, in principle, I just want to mention that if this is what you get, like what it means. Let me write just it in a bit more appropriate form, and then I will explain what's the meaning of this. Okay, if I have this map, so your RGE reduce almost to just a basic initial problem. Okay, that's just nothing. This is trivial. But in fact, you really need to work a bit in order to get into this basis so that you arrive into this system. What it means, there is this kappa parameter, I will be more precise, which plays the role of the effective coupling in the model, and the S is the parameter that deforms your geometry. What it means that you have two regimes, like, so S is between 0 and 1, okay? Sure. Yeah, that's what I'm saying, D to Z. Yeah, that's my signal. Well, I think I was doing something. Yeah, but what Pavel is asking is the following. Yeah, very good. So when my S is 0, my target is sphere. Oh, I apologize. S is 1, so this is IR. Okay, S is a deformation parameter. It's in a different. This is what I'm saying. I passed a different parameterization. This is why S. I will write in a second how it arises in this new basis. What I want to say, what Pavel is asking is something. Let me state it the other way around. Okay, now it's important. So when my S is 1 or my S is 0, what happens to my geometry? I'm a bad drawer, but okay, I hope it's comprehensible. Anyway, sorry, I think that's the other way around. Yes. So this is a sphere, and this is, I don't know, I don't like this name, but this is what people call sausage model. Okay. Yeah, and so you flow in this direction because this is UV and this is IR. And that's the geometric interpretation of what is happening. So this is how curvature of what? Like a scalar curvature can be expressed in terms of this 1 over S. Oh, sorry. You mean probably in terms of this?
Depends on position, so it's space.
Sure, but
Here it could be one. I mean,
sure, but here it's. I prefer to think like in this form. This is how it describes how your deformation parameter depends on this kappa, because some I think initially they derive this curvature in terms scalar curvature in terms of this kappa, which in their terminology is some ratio of these A's and B's. But okay, let me write this down. Okay. So eventually, okay, maybe let me skip. You can acquire, of course, you have the corresponding metric of your theory, and you can acquire it in an explicit form, which will be dependent on certain bosonic fields and these parameters. But for today, what I want to say is that I will be mainly staying. Like you can, there are two types. You can study the sigma models similar to this, whose target space is symmetric, and which includes like complex projective spaces and Grossmanians, or you can study non-symmetric, which will include like flag manifolds or quiver varieties. But my point today is that I want to see first a prescription which is more suitable for the like interacting models, interacting integrable sigma models. Okay, then another important point, I want to see my beta function from perturbation theory, if you want. So without any background field methods, okay? And at the same time, I want to have a consistent supersymmetrization scheme, as I mentioned already. So these are three main motivations. There are many other, but these are the main ones. Okay. Let me conserve a bit of time. What I will be concentrating on is the following. Sorry, is that big enough? Okay. So what I want to say is that my model, something that I will be concentrating on, one can ask, how is it different from the, say, CPN -1 model? And the answer is that 2 over this kappa, and this is covariant. Okay. Apologies. Of course, minus. Yeah. Okay. Yeah. Thanks. So, which is nothing but, as you could have noticed. So, so this is A from one to n, and here now. Okay. Let me see. A, and this is okay, mu, which is antisymmetric, and this Remarkably, which is nothing but the antisymmetric two form, right? Which is just Fubini's study, Fubini's study form. Okay, what it means that these two series at the classical level are equivalent. Of course, when you start quantizing or adding like topological terms, then you immediately will run into problems, because, well, in other terms, maybe, I don't know, I can write it probably also in this form. U is your bosonic field. Say it again. In principle, yeah, exactly. It's a column. Like, it's a vector. Hmm? So what I want to say. Twice bigger. Yeah. I will try. Okay. So what I want to say is that now, since, like I said, I will be concentrating on this, so that the two series just differ by topological term. Okay. At the classical level, it makes no difference. So what I want to start from is like if I. No, I recapped the deformation. I will show you now what I want. Yeah. That's already deformed. This is sphere is undeformed. Fateev-Onofri-Zamolodchikov, this is like O3 or CP1 with a one parameter deformation. So now this at the moment I have not specified. I'm coming to it. Okay. All I'm saying that some Lagrangian. I want to make the point. Some Lagrangian. What I'm going to talk about will differ at the bosonic level just from this by topological term. Okay. Let me show. Okay. So what it means, just, yeah, let me recap. So this is like you have a beta gamma system, okay? Now what you can do, turn it into BC beta gamma. There are, of course, different ways one can ask, like Pavel was asking, how do you extend this, supersymmetrically extend? You can have minimally coupled fermions. You can have supersymmetrically coupled setups, but the main more convenient way is that. I hope you can see this. Okay, which can be, of course, further compactified into. Like, let me be more precise. Okay. Yeah, where this curly is U, previous U and C, and this is V and B from here. Okay, I have just rewritten, nothing else. That's boring. What I want to say. Yeah, and in this case, yeah, the target space symmetry just encapsulated here, okay, where, yeah, this G is here. Okay, let me mention two things, but now, of course, what I want to see is that all this is good, but These are partials. Okay. If I want my goal is to supersymmetrize this CP model, I need to covariantize. If I covariantize, you still it will become manifestly non-supersymmetric. You will need to prove this. So that's one disadvantage, but there are other main advantages of doing it this way. So I just keep in the old terms rewriting it just for consistency. Okay. Okay. No. Okay. But now you of course have this plus whereas now this is already, for the moment I just say this is the gauge field, but I will specify. What I want to say is that even at this level, you would need just to recall, of course, let me just, yeah, epsilon 1. Let me write this. So this is a canonical stuff. Minus epsilon 1 v, yeah, then delta. Oops. Yeah, delta c is minus epsilon 2 du. And delta v is, yeah, epsilon d db. Okay, so the, yeah. That's what I'm saying. I'm extending. This model is just purely bosonic. From here you cannot see what's from here you cannot see. This is yes, which are bosonic. Yeah. From here you cannot immediately see, but this is bosonic. There, x and y, there is the play the same role as v and u here. But yes. Of course not. Of course not. I have not. Of course not. Yeah, I'm coming to this relation. Of course, this is not. As you see, this is purely covariant as beta BC beta gamma. It still doesn't have any interaction. In order for them to be related, I need to add something else. I'm coming to it. At the moment, I'm. No. Sorry, not to confuse. This is I have recapped of the deformation, bosonic deformation that is canonical of the sigma model. Here now I'm saying that I will be starting the model. I'm deriving it. The model which I want to start from the beta gamma system and derive a supersymmetrized version of this model. So not to confuse, yeah, Pavel made good point. So this is just, I recap what is the notion of the Ricci flow and how the CP models develop. I start from some Lagrangian, which develops from the bosonic CP by topological term. And then I'm developing the structure to first supersymmetrize this beta gamma by BC, and then add something which will deform, which will play the role of deformation. I'm coming to it. Okay, what I want to say here, you cannot naively just take this, supersymmetrically extend by bosons and say, okay, I have a supersymmetric model. It doesn't work like this. Because if you want to have proper complex projective space model, you need to covariantize. And then you will need to explicitly show, like I'm saying, this is by the standard stuff by Friedan and Tal, Kapustin, and yeah, I think Ed Witten from the 2000s. This BC beta gamma you can show immediately, but when you add, yeah. Yes. bosonic. Yeah, they're vectors. Sorry, good. These are vectors, like column, like you said. Like if CPN and column. Very good, very good. You very good. You are coming. You are anticipating the very right point. These second order constraints. I'm coming to it. There will be condition. Very good. The point, the claim I'm making now, I want to consistently demonstrate and derive how you start with something like completely integrable, like beta gamma and well-defined, how you extend supersymmetrically coupled deformants, propose to the complex projective. Okay, I'm eating many stuff due to lack of time, but what I want to say that with these supersymmetric transforms, like you said, so these UVBC, they transform supersymmetrically like this. If I use this on this BC beta gamma part, this is trivial. I can prove that this part is supersymmetrically invariant. But if you add the interaction, then you are in trouble. Well, there is a way to cure this, but yeah. So let me just recap two things. Q plus, yeah, plus epsilon. And this is probably more or less known. And so their closure is that this is partial, and this epsilon 1, 2 are just Grassmannian variables. Okay, what is this? This completes for you just one holomorphic part of the supersymmetry algebra. If you write the second part, which is on the anti-holomorphic components, you will get 2,2 supersymmetry, super algebra. Okay. And now, so coming to the Pavel's point, what I want to have now is the following. So I have some action on certain Lagrangian, where LS is, now I continue in this, writing this compact form. No, it was before. Okay, yeah, this is 2. So now let me explain. So that was, like I said, BC beta gamma compactified into this, I don't know how they call this, curly U and curly V, which contain, just to notice, both are fermionic doublet. So this is super doublet, which contains bosons and fermions. Now, I have added an interaction, which is bilinear in this component. So this is the what is called in GLSM moment map. But in fact, something maybe to be more familiar, so this is nothing but the Kac-Moody current. In this case, we are going to discuss today. Okay. So this mu is U tensor V minus CB. Okay. So what it means, so you have, as if you multiply this, you will be, of course, anticipating, since every current is bilinear in this UV, not the curly, but these ones. So it's quartic, and that's essentially quartic interaction. Somebody probably can notice like having a 5-4 analog in 2 dimensions. Okay, but now there is one more important point, is that now this the covariant derivatives that you have here is plus I, and now this is S. AS. So this is super connection. Now this is a super gauge field. What it means that this AS is, you would be anticipating like this, something, but now you have extra fermionic degree at the lower bottom, so lower triangle. Okay, and this W, it's like, I don't know, it's, you can interpret it as like additional Lagrangian multiplier. Okay, but now, of course, addition of this will induce additional or sorry, was I writing here? Or, yeah. Okay. So this W, it imposes, after you can check, of course, this explicitly, it imposes what is called, yeah, I think second order constraints. Pavel, did you mention something like this? Or so you can have this one, but at the same time, you will also have, sorry, yeah. Now the scalar, because these are these are vectors, and when you multiply, so this is a matrix. Okay. Sorry, what am I? So these two constraints will play an important role. No. So your additional, like having this fermionic degree, it induces these constraints. And these constraints will be important if you actually want to prove supersymmetric invariance, because like I'm saying, in the form, okay, yeah, I have written here, it's not manifestly supersymmetric, you need to prove this. And in order to prove this, okay, let me skip a few things. But what I want to say now is that imagine on top of this, like, okay, let me write LS. Let me just be sketchy a bit, okay, due to time conservation. So you have BC beta gamma by this, yeah, I mean, by BC beta gamma, let me call this thing, also, I might be a bit more precise, plus kappa over 2. Now I want to deform my interaction. How? By a certain object, which acts, whose action on the operator can be defined in this way. Yeah, let me write it maybe. Okay, in this form, it's a bit more convenient. So this is 1, 1. Square root, 2, 2, 1. And this is half 1 plus s. Okay. So that's a factor action. This is nothing but. So this is a certain operator which acts, certain action which acts on the operator, just shooting up certain parameters. Okay. The reason is that I recap. These are currents which are in fact like matrices. So I want to deform one of my currents. That's a long story why I should consider this and not something else, or maybe in combined form. But what I want to say is that this object that is involved here, okay, I can in principle rewrite it in, let me call it a bit modified form. This S plays the same role of the S that we have been discussing, this canonical Fateev-Onofri-Zamolodchikov. This is deformation parameter. Okay. What I want to say is that I have this relation here, and here is identity. I'm not commenting why I can exactly write it in this form, but the point is that this object R, this is the one that will satisfy classical Yang-Baxter equation. So again, this RS, if you just recast it in these terms, it's of course a separate conversation what and how it implies, but what it means. Let me write and then I just give a comment. Okay, anybody for the classical integrability would expect this so that you have flatness condition. All this is good. But now this, okay, let me write it. There is a way how I can define it in terms of this classical R matrix, when this shift parameter here, whatever it means, is 1. So my connections can be defined in terms of this RNS, which is arising here. So I can build up my connections, and which will satisfy the flatness condition. And due to okay, whatever. Within Castellani and Mazzocchi, it implies that you also have CYB. Why? You can see the proof in their part 1. So what it means in this deformed setup that I have been describing here, I can explicitly construct the connection which will satisfy the flatness, the zero curvature equation. Okay, which is that. Okay. Okay. So now let me recap. All this is very good, but let me say a few words about. We can prove that this is integrable. How about super-invariance? Okay, of course you can do the standard variational problem. And after many things, let me just say let me bring you just the most important part. Okay, so I have the same kappa, so this mu is the moment map or the current that I was describing. Okay. Okay. And of course, I'm getting the doubled. So holomorphic and anti-holomorphic currents with just the sign change, and I have this RS just deformed the first one, then the bar here. Okay, I'm getting these two equations. So these are equations of motion on moment maps, so on your currents, and they will play an important role in the case that, like I said. Now I would like to make it schematic so to convince you that this is indeed supersymmetric. You keep in mind these transformations. You can derive these moment map equations. These transformations can immediately, you can do it implicitly that this BC beta gamma is super invariant. But when you do this, how about interaction, which is, I would say, the most important part, of course. On the bar. Okay. What do we get? This can derive in this form. This is mu tilde. I will mention. This is mu. And this is the commutator times mu bar. Yes. This mu tilde here is nothing but, this u cross b. This is what comes from the derivation, and the variation of the current itself ends up in this one of these Grossmanian parameters with du tilde. Okay. Yeah. So these two, you end up in this. You want this to vanish, of course, in order for the theory to be supersymmetric. How? I look into this commutator. So this is what? This is R mu tilde, RS, R mu. Okay. And let's see. What is this explicitly? Let me be very quick. Okay. What do you see? You see second order constraints exactly in each, so they vanish independently. Indeed. Okay, now Okay. Now, provided I have this thing, I want to understand. So I have a kind of, okay, BC beta gamma interaction model, which is supersymmetric, which is integrable. All this is good, but can I find what's geometric meaning of it? So geometric interpretation. I can start by passing to the what is called inhomogeneous basis. What does it mean? So you can do you can take as partially certain gauge fixing, which is an allowed gauge fixing. This so yeah, I apologize. One important point. When I pass to here, I'm starting to talk about this particular case when n is equal to 2. So this is CP1. Okay. So, and I just recap. So any U is like Pyle was saying. So this is like a column vector. This is what you have. But now I have two components. So this U1 is exactly the corresponding component. And I can find like a gauge fixing for these two. You use this, plus I'm trying, yeah, to mention what it means to pass to you use these constraints. You combine them together and eliminate certain components, so you solve your UVBC vectors in terms of this fixing. Okay, let me skip one part, but now, okay, so it means like you get something like 1 over U here. There will be now this U is the second component of U, so I will denote them by small letters. Okay. So effectively, you will end up in something of the following. Okay, let me see. So this is, let me bring this like that so that you can see the full part. E plus. Okay, let me write. Okay. And now you have beta squared alpha U squared C B bar C bar. Let me, due to time, let me do the following. Let me tell you. Okay, this omega is the most important part. So this is our good kappa. Okay, you have half plus, sorry, minus the plus 1/2. Okay, this S is our deformation parameter. So this omega is like a deforming parameter for you. Now, of course, this alpha, okay, this alpha, beta, gamma, let's mention these are functions of this kappa S. These are all kinds of rational expressions that I just don't bother to write you, not to lose the track of the main point. Okay, so these are exactly the functions which you can find in their ratios. Okay, so this is like work parameter. Okay, so now what do you have? So this omega is like here inverse to this one, and this alpha sits here. At the same time, oh, I want this to be here. Okay. At the same time, I know that my LS, my supersymmetric 2,2 supersymmetric Lagrangian, if it is, since this is, okay, so this is scalar. Another important comment. When you pass to, say, greater than 1, starting from 2, this is what is called generalized scalar. And for the moment, we don't have a rigorous proof of its supersymmetric invariance. There is really something special starts to happen. So what I want to say that at the same time, this scalar models with 2,2 symmetry, they have the following form. I look at this too. I look at this Lagrangian and and this Lagrangian, which comes from the like I said, 2,2 scalar systems. Okay. So, sorry. Big R. This is Riemann tensor. Very good. Somebody is anticipating. In fact, this is, of course, I'm writing generic form. In fact, of course, it is not, because there is just one component that is left. Which manifold? Yeah, sure. You talk about your target space. Yeah, but here, yeah, CP1. Let me say, deformed CP1. Very good. So something that Andrei anticipated. This is, in fact, is just Ricci scalar, and the reason for that, because the matrix that stands here is of this UU bar. Sorry, I should have mentioned one more thing. So, yeah, scalar curvature. So what I want to say here, I should have mentioned, how did I pass from something like this with U and B by fixing, and why there is just one U and not where is V? I have extremized with respect to one of the fields. So we resolve this, substitute back. So you extremize with respect to one of these V's. So you really end up with one U, which is bosonic, and BC, which have the role of ghosts. What it means, it matches. If you open, this is according to Vafa-Hori derivation. This is the type of the Lagrangians that you get in the mirror representation. But the point is, like Andrei was mentioning, in fact, since this is just UU bar metric here, this is just Ricci scalar. And here you just have this UU bar twice. I just wanted to show you the exact match. The point is that now I can see explicitly that this model falls into this class, which is in principle highly non-trivial, because these models have a good mirror interpretations. U. Well, Berish, I was mentioning, when I was fixing, I was having this. This is this U. When I fix, so this is the second component of capital U is having big U1, big U2, like a vector. When you fix this with these ones, you will get that you will get this prescription. You can get. This is what I want to have. Bosonic. No. U has big U was having like CP1 has two components. Small U is a component of big U. So this is already in component form. One, just one. That's the point. So, okay. In CP1, you agree with this? Here, U has U1 and U2. You did the fixing, you have arrived at one, and this. That's all. So this is already in this. But the one non-trivial thing is, of course, you can be happy to have this, but in principle, this D bar, say on C, the ghost, D bar C plus B over alpha, U bar, D bar U, and C. This is Christoffel. And this Christoffel must be consistent. Sorry. Was that? If it is not, so you need to check this independently. And indeed, if you do this operation with this metric in front, you recover the correct connections. Yeah.
If I forget about B and C,
Okay.
is this a signal model?
Very good. Very good. What is this object? This is bosonic Fateev-Onofri-Zamolodchikov. See, I'm telling you, this GUU bar is exactly Fateev-Onofri-Zamolodchikov. Exactly. So this is deformed sphere. This is sausage model. Very good. Exactly. I'm just, you see, yeah, I understand. Yeah. So can I continue? You get a consistent. You get a supersymmetric sausage first. Yeah, as Zoltan Beinek and Chang Riemann called it super sausage. Yes. This is what we get, but you get field theoretic description in terms of the BC beta gamma, and you get a geometric interpretation, which is consistent with n equals 2 Landau-Ginzburg models. Okay, since Andrei mentioned I have really 5 minutes, let me mention something what is mostly interesting. Okay. Now, we have this in mind. What I want to highlight here is the following. So, as I mentioned, all this is good, but now how about like gentlemen in the past, like including Zamolodchikov, for studying the UV conformal limits when you send this deformation parameter to something, and you will be recovering 2 types of models. So let me sketch 2 things for you. So there is a sigma model, and there is, let me say, chiral model. Okay. What I'm talking about is the following. When again, let me say this and this, because this is from the chiral type. So I have in terms of currents and so on, but here this is like a geometric form. So from okay, let me be explicit. So this is SM, and this is the chiral QFT. Okay. What I want to say is the following: that you have 2 possibilities. Possibility 1 is that you take your small u and send it to you rescale it to quarter of s of u, and then send s to 0. What you recover is what is called supercigar. Okay. Yeah, but here we don't have a name. This is new. So this is scaled Gross-Neveu, certain type, supersymmetric one. Possibility number 2. You can immediately send S to 0 from this one, and this is what you get as a super cylinder. So this is model on S cross R1. And here, you get the supersymmetric Thirring model. Okay. Now you have like a kind of dual descriptions. One in terms of the chiral fields, and the second one in geometric. So now the point is, okay, let me mention this. So this of the super cylinder, this would be 2 over kappa. d bar u squared plus b d bar c minus c bar d b bar. Okay, that's a reduced Lagrangian on the geometric side, and supercigar is having some additional terms which is more involved. Geometrically, it means these two models. Like if you send S immediately to 0, imagine now you have this what is called CP1 deformed model, like a sausage. You are somewhere in the middle. You take S to 0 and you remain in the flat space of the cylinder. So it means like decompactifying. If you take S to 0 immediately, it means you end up exactly in this model. This one, if you deviate towards these tips of this super sausage, then you rescale S and then take S to 0. You end up exactly around the perturbatively around this tip, and this is why you see this cigar curvature like with a conic singular point. Yeah, but the point is, okay, let me maybe just say this in words, because I'm happy to show this explicitly. What we, in the case of the supercylinder and the super-Thirring, how do you prove? You would want to study either algebra or compute observables. So we compute like 4-point functions and others by two independent methods. Here you can of course do like fine diagrammatics, like perturbation theory, and you can derive a 4-point function of mixed primaries like bosons and fermions with Koban-Nielsen factors. Here, and you end up with something that is, I can show the details, but you end up with something that is proportional to what is called the SL2C cross-invariant cross ratio, SL2C invariant cross ratio. Here, at the same time, completely independently, you take this supercylinder model, construct your vertex operators, and do the functional integral approach by deriving the equations of motions, substituting back, and you end up exactly with the same 4-point function to L loops. So this is just one part of the correspondence, but then we are now working on this. And I can also, maybe let me just mention, like a future, a kind of, there is other thing which I'm looking at now. There is a theory. So this is the standard Chen-Simon theory in 3 dimensions, which you can extend by what is called. This is that. So this is meromorphic one function, which is meromorphic one function, and this is one form which parameterizes this C curve, and this is a 4D setup. So this is like a four-form theory, and you can start introducing certain types of the defects in this theory. One remarkable point that when you integrate out, do like a topological dimensional reduction, integrate out if this sigma appears to be complex projective, you integrate out. I can derive this generalized supersymmetric model, but that's of course a very big story because first you need to construct supersymmetric 4D Chen-Simons. Yeah, and then you can study actually many different things. If you have just ordered defects or disordered defects, this is UV integrable field series, or you can introduce Wilson lines on these defects, and then you will get discretization scheme. This is what was studied by Yamazaki and people. But then this is integrable pinch and picture, and this is IR description. Okay, sorry for overtime, I stopped here.
Okay, dear colleagues, some comments, questions, maybe by Zoom, not? No? Oh.
Off. Right. I apologize, I didn't have time to describe the beta function, but you're right. The point is we have got to 3 loops, and we see only 1 loop contribution. But the point is that from the 4 loop, as you know very well, you start getting this renormalization scheme dependence. But the claim is There is no rigorous proof that this theory is one loop renormalizable, like to all loops. But that's still a conjecture. But the point is that I didn't mention there is like a parallel ongoing computation where people for the same similar construction, very similar construction, like Fateev-Deformed, like Litvinov and people, they have been looking at this beta function from the like independent renormalization scheme constructions by certain like geometric method. They got, as far as I know, to 4 loops and maybe now already 5, and they still see 1 loop contribution only to the beta function. So it's maintaining like to be one rule. Yes. Actually, very good, because if you put, for example, S equals 1, this is a sphere. This is like IR, IR fixed point. And there is still no rigorous proof, like to be one loop renormalizable. But it's much easier to study this renormalization group equations and the conditions at each loop level. And actually, I can refer to, I think Dima Bykov was studying a few years ago the setup, and he was getting to 4 loops. But again, at the 4 loops, you get this rect scheme dependence at certain loop level. It depends, of course, which scheme you choose, but it seems like there is a universal feature. Like when people, this Weinstein and company, when they were studying this beta NSVZ beta function, like in 4 dimensions, they were facing similar phenomenon. But their rect scheme dependence was arising at 3 loop level. There is something similar, very similar happening, but in 2 dimensions.
Okay. Let us thank our speaker again. Okay. At the next